So the statement of the question here is, in the circuit below, assume that the long channel NMOS transistor is biased in saturation full stop. The small signal transconductance of the transistor is GM full stop. Neglect body effect, channel length modulation and intrinsic device capacitances full stop. The small signal input impedance Z in terms of J omega is. So this is the question they had asked in GATE 2024 for EC branch, and this is the question taken from this analog circuit. So here this is the figure it has given. In corresponding to that, we have to find out their Z in, and their option is given in ABCD. So here, as per the procedure to find out this Z in, we know that this Z in is defined here. This Z in terms of J omega, this is defined here as a voltage by current ratio. So here we have to take some test voltage across this input terminal from which we are going to find out this Z in, and due to that test voltage how much current it is passing through this circuit, so that ratio of voltage to current is giving here as a Z in value. So that we have to find out their expression. So now I am going to draw this circuit again by taking the help of the small signal parameter. So first of all, we have to draw the small signal parameter of this MOSFET, and then as per the element connected here, we have to connect that and complete the circuit. After then we have to find out this Z in. So first of all, we will draw this circuit here. So this I am taking here gate terminal of this MOSFET, and this side I am taking here as a drain terminal of the MOSFET. And if you see that in the original figure, this drain terminal is connected, their other terminal is connected to the ground, and this will be acting here as a dependent current source which is flowing from drain to source terminal. So this is the dependent current source, and here we can take their source terminal. So as per the circuit, if you see that here we have that from gate terminal to source terminal, if you find out that there is one capacitor connected which is called C1 capacitor, so that we can connect here. This is C1 capacitor, this is here C1 capacitor, and from this source to ground in between also there is one more capacitor connected which is called here as a CL. This is a CL, and this terminal is gate terminal, and here it is source terminal. So the voltage appeared between gate to source, it is called here as a VGS. This is plus here, this is minus here, so this is VGS. And as we know that this current passing through from this drain to source, so that is called dependent current source, or that is called drain current. So it is given here, this ID is GM VGS, GM VGS. So now through this input terminal we have to connect what? We have to connect here the test voltage. So I am taking this test voltage as a V. This I am taking here as a test voltage V, and due to this test voltage the current flowing is I. So from this terminal we have to find out Z in. So this Z in, which is the function of J omega, is given here as a test voltage V divided by, due to this voltage source how much current is passing through this circuit, so that is given here as a I. So this V by I ratio is giving this input impedance. So let's say this as equation number 1. As we know that this capacitor is also the function of frequency under the AC analysis, so here their impedance will be given, as a 1 by J omega C1, and for this one it will be given 1 by j omega CL. So if you'll see that how much voltage will be appeared across this C1 capacitor, so that voltage will be referred as a gate to source voltage. So if you'll see that this I current which is coming from this voltage source, it is passing through this part. So this is here I, and this I is coming till this S point, and from here, from this drain terminal, the current coming is GM into VGS. So this both is joining here, and the current passing through this CL will be what? The current passing through this CL will be I plus GM into VGS. So here we can say that this VGS will be what? This gate to source voltage VGS is equal to that this impedance into their current will be the voltage across this C1. So I can say that this VC1 voltage appeared across this C1 capacitor is equal to VGS, and that will be given here I into 1 by j omega C1. Let's say this as a equation number 2. So now we have to apply the KVL to this input side, the KVL to this input side of the circuit. So then by applying the KVL at the input side, what we will get it here? Apply KVL at input loop. So here, if we write down their KVL, then we will get it here minus V plus I into 1 by j omega C1 plus I plus GM into VGS. So both the current will be added together into 1 by j omega CL is equal to 0. So here we can rewrite the same equation here, that minus V plus I into 1 by j omega C1 plus I into 1 by j omega CL plus GM into VGS into 1 by j omega CL is equal to 0. So now from this equation number 2, we can substitute VGS in this equation. So what we will get then? So if we substitute the value of VGS from that equation, then we will get it here, that minus V plus I into 1 by j omega C1 plus I by j omega CL plus GM divided by j omega CL into, in place of VGS, we will get it here I by j omega C1 is equal to 0. So as we know that j into j will be j square, and j square is equal to what? As per the complex number system, it is minus 1, and omega into omega, it will become here as a omega square. So we can rewrite this again here. So this can be written minus V plus I into 1 by j omega C1 plus I by j omega CL minus, so this j into j, it will become j square, and j square is equal to minus 1, so it will be minus sign here. So minus GM into I divided by omega square CL into C1 is equal to 0. So now if you rearrange this, and if you take the ratio of this V and I, then what it will become here? So by taking this, by rearranging this, and if you take it the ratio of V by I, so this V by I is equal to 1 by j omega c1 plus 1 by j omega cl minus gm divided by omega square cl into c1. And as I had explained earlier, this v by I ratio in terms of this omega, it is giving here as like j omega. So this is j z in j omega. So this is the function of j omega. So due to that reason, this z in is written in terms of j omega. We got this ratio here. So we got the ratio, like we got this expression z in is the function of j omega is equal to v by I is equal to 1 by j omega c1 plus 1 by j omega cl minus gm divided by omega square cl into c1. If we'll compare this with the option, then it is matching with option A, minus gm divided by c1 into cl into omega square plus 1 by j omega c1 plus 1 by j omega cl. So due to that, we can say that this option A is the right answer for this question. By this way, the explanation for this question is over. Thank you. So the statement of the question is, for the closed loop amplifier circuit shown below, the magnitude of open loop low frequency small signal voltage gain is 40 full stop. All the transistors are biased in saturation full stop. The current source ISS is ideal full stop. Neglect body effect, channel length modulation and intrinsic device capacitances full stop. The closed loop low frequency small signal voltage gain V out by V in, and it should be taken round off to 3 decimal places is fill in the blanks full stop. And this is the circuit given for this question here, and their option is option A 0.976, option B 1, option C 1.025, option D 0.488. And this is the question is taken from this GATE EC 2024 from the subject of analog circuit. So now if you observe this circuit very carefully, then you will find out that this upper portion is current mirror circuit. This portion is current mirror circuit, and lower part it is showing here as a differential amplifier. So this current mirror circuit is used here for the biasing of this differential amplifier, and combinedly this can be treated here as a operational amplifier in the, this can be treated here as an operational amplifier here. So if you'll see that as per the information given here, their open loop gain is, their open loop gain it has given their open loop gain, let's say A is equal to 40. And if we are treating this as an operational amplifier, so let's see this under the closed loop configuration how it will appear. So this will appear like this. So here this is input terminal, we can say it here. This is the input terminal. This is non-inverting, and this is inverting here through which feedback is given, and this is here V out, and here by default we can consider their beta, which is called feedback gain, is equal to 1. So as per the information given in the question, if we will treating this as a op amp, then we can easily find out their closed loop gain, because their open loop gain is given here as a is equal to 40. So if you'll see that their closed loop gain will be what? Their closed loop gain, their closed loop gain is equal to A, that is called the open loop gain, divided by 1 plus A into beta, where beta is called feedback gain, or we can say that it is the feedback network gain. So here, as per the value given, this open loop gain is 40 divided by 1 plus 40, and beta by default we are taking here as a 1. So this will become here as a 40 by 41. So this is giving the value here as a 0.976. So this value is matching with option A. So option A is the right answer for this question. And by this way, this is the end of the explanation for this question. So the statement of the question is, in the circuit shown, the N is to 1 step down transformer and the diodes are ideal, full stop. The diodes have no voltage drop in forward bias condition, full stop. If the input voltage in volts is Vs, which is the function of time, is equal to 10 sine omega t, and the average value of the load voltage VL, which is the function of time, in volts is 2.5 by pi, the value of N is, fill in the blanks, full stop. And their option is also given. Option A is 4, option B is 8, option C is 12, option D is 16, and this is their corresponding circuit, whatever it has given. This is the question they had asked in GATE EC 2024, and this question has taken from the analog circuit subject. So now if you observe this circuit here, it is center tap full wave rectifier circuit. For that circuit I have to analyze first. So this side it is called primary coil and this side it is called secondary coil, and their number of turns it has given as a N is to 1. So in which we have to find out this N value. So here if you see that it is given step down transformer. Step down transformer means their primary number of coils will be more compared to their secondary number of coils. So here we have to find out the value of N, how much it is larger than this secondary. So that we need to find out here, and their information it has given this Vs, which is the source signal, is given as a 10 sine omega t. So the voltage appeared across this primary coil we can consider here as a V1, and the voltage appeared across this secondary coil we can consider this V2. So if you see that if this is here center tap means here it should be somewhat ground. So if you see that whatever voltage appeared across the secondary coil, that will be dividing into two parts. So ultimately whether D1 is conducting or D2 is conducting, the voltage appeared across this RL, which is called voltage is VL. So that VL voltage, like the voltage appeared, basically it will be half of the secondary voltage. So here as per the relationship between number of turns and this voltage appeared is, we can say it here, this will be given as a V2 by V1 is equal to N2 by N1. This is the relationship between voltage and number of turns ratio. So here this V2 is the voltage appeared across secondary coil and V1 is the voltage appeared across primary coil, and it is related by the number of turns. So number of turns for the secondary coil, it is given here as N is to 1. So this will be 1, and the primary coil is having the number of turns is N. So this is giving here as a V2 value. So what will be their V2 value? V2 is equal to V1 divided by N, and V1 it has given in the question. So V1 is what? The voltage appeared across the primary coil. So whatever we have this Vs, this entirely will appear across this as a V1. So this V1 is 10 sine omega t divided by N. Let's say this as a equation number 1. So as I had explained, it is a center tap transformer. It is a center tap transformer. So voltage across load will be what? Voltage appeared, voltage across load is equal to V2 by 2. So simply V2 is what? 10 sine omega t divided by 2n. So this will be giving here as a simply, this will become here 5. So 5 sine omega t divided by n. Let's say this as a equation number 2. So this V2 voltage, like whatever voltage it is appearing here as a 5 sin omega t by n, it is not the average voltage. So whatever we are talking, it is the normal voltage appeared across this load. But here, as per the information given in the question, it has given their average voltage here. Average voltage appeared across this RL is VLT, whose value is given as a 2.5 by pi. So whatever we got the voltage appeared across this RL, we have to find out their average value in terms of n, and then we can easily find out the value of n. So here we can say that this given average value is given V average value is 2.5 by pi. And as we know that for the full wave rectified center tapped, their average value is given 2 Vm by pi. Their average value is given 2 Vm by pi, and the average value given in the question is 2.5 by pi. So this pi and pi gets cancelled, and we will get it here 2 Vm is equal to 2.5, and whatever is the voltage appeared across the load, so that voltage is given here as a 5 sine omega t by n. So in this one their peak value will be 5 by n. So we can substitute here their peak values. So their peak value will be 2 into Vm is 5 by n is equal to 2.5. So from here we will get this n is equal to 2 into 5 divided by 2.5. So this 2.5 and 5, it will give it here 2. So now we will get it here 2 into 2. So that is equal to 4 here. So we got it here n is equal to 4. The number of turns at the primary coil is 4. So here we can say that the right answer, whatever it has expected to find out the value of n, which is the number of turns for the primary coil, is 4. So that option A is the right answer for this question. And by this way, this is the end of the explanation for this question. Thank you. So the question here is, the op-amps in the circuit shown are ideal but have saturation voltages of plus minus 10 volt full stop. And this is the circuit given here. And rest of the statement is, assume that the initial inductor current is 0 ampere full stop. The input voltage Vi is a triangular signal with peak voltage of plus minus 2 volt and time period of 8 microsecond full stop. Which one of the following statements is true? Question mark. Option A, VO1 is delayed by 2 microsecond relative to Vi and VO2 is a triangular waveform. Option B is VO1 is not delayed relative to Vi and VO2 is a trapezoidal waveform. Option C, VO1 is not delayed relative to Vi and VO2 is a triangular waveform. Option D, VO1 is delayed by 1 microsecond relative to Vi and VO2 is a trapezoidal waveform. And this is the question they had asked for GATE EC 2024 from the subject of analog circuit. So if you'll observe this circuit here, the first part of the circuit here, it is showing that VO1 is the output of the first op-amp and VO2 is the output from the second op-amp. So the first part of the circuit is very much clear that it is a Schmitt trigger. It is a Smith trigger with non-inverting input. So here this first part is a Smith trigger circuit, and as we know that the functionality of a Smith trigger circuit is it will convert sine wave or triangular wave into their corresponding square wave. So as per the option, first part of the question, it is like first part, it is asking that whether the input given here is triangular waveform. This input is triangular waveform like this. So here corresponding to this triangular waveform as a input, whatever is their square wave, whether it is delayed or not. If it is delayed, then we have to check it with the option A, whether it is delayed by 2 microsecond or whether it is delayed by 1 microsecond. So that will give you the answer for this one. If it is not delayed, then we have to check it with option B and C. So, and then as a second part, whatever is the square wave coming from the output of the first op amp, it is giving to the second stage. It means as an input to the second op amp. So if you observe that here integrator like this inductor is connected at this place. So here it is saying that the second portion of the circuit will be an integrator circuit. So whatever will give the input to this terminal as a non-inverting input, so this will produce their output. So that output waveform also we have to find out as a second portion of this question. So here first of all have to analyze from this one, from the Smith trigger circuit. So first of all I'll take it out as a non-inverting Smith trigger circuit. So this will be look like this, and here we can easily find out their upper trigger point. So here their upper trigger point which we can denote this by the UTP, and this will be given here as a R1 divided by R2 into plus Vsat. So here this R1 value is 10K divided by R2 value is 100K, and plus Vsat is given here as a 10 volt. So after solving this KK gets cancelled and this will become 100 by 100. So this is giving here that UTP, that is called upper trigger point, will become here as a plus 1 volt. So what do you mean by this? Whenever this input signal is crossing to this point on the waveform, then by that time that status of this output VO1 changes from minus Vsat to plus Vsat. So here this is saying that previously it was at minus Vsat. Whenever this input is crossing to this upper trigger point, by that time it is going to change from minus Vsat to plus Vsat. So here we can write also, if Vi goes above plus 1 volt, then VO1 transits from minus Vsat to plus Vsat. Similarly, we can calculate here as a lower trigger point. So lower trigger point will be what? That we can denote here as a LTP. So here we can write it R1 by R2 into Vsat with minus sign here. So this minus sign is because of minus Vsat. So here we can substitute now this minus. R1 is 10K, R2 is 100K, and here this will become 10 volt. So after doing this calculation, this will become here as a minus 1 volt. What it is saying? When this input, or we can say it here, if Vi goes below minus 1 volt, then V output 1 transit so this is going to minus 1 volt. It means previously that output of this op amp as the VO1 is at plus Vsat. So now it will transit from plus Vsat to minus Vsat. Plus Vsat to minus Vsat. So by taking this UTP, LTP and the peak point of the input as a triangular waveform it has given in the question, we are able to draw their corresponding waveform like this. So here if you'll see that this is the triangular waveform whatever it has given as an input. So basically this is the input waveform here and it has given their peak is plus minus 2 volts. So this is minus 2 volt, this is here plus 2 volt and it is having the time period of 8 microseconds. So to complete one cycle here it is taking 8 microseconds. It means to complete half of this. It means what I am trying to say that to reach from minus 2 volt to plus 2 volt and again coming back to minus 2 volt is completing one cycle. It means how much time it will take to goes from minus 2 volt to plus 2 volt. It will take here 4 microsecond. It will take it here 4 microsecond. That will be half of this complete duration because at this point it is going to complete half and this is plus 1 volt is there UTP and minus 1 volt is there LTP whatever I had shown here. So if you'll see that what is the time to cross this zero line. So this is here 0 volt line. This is the line whatever I am showing here. It is called 0 volt line. So the point wherever it is crossing this it is called ZCD, zero crossing detector. So at this point at how much time it is crossing this ZCD here, it means this input is crossing the zeroth line by how much of time. So if you'll see that here minus 2 volt to plus 2 volt it is having the swing of 4 volt. So to reach from minus 2 volt to 0 volt, it means it is having the swing of 2 volt. So how much time it will take? It will take here 2 microsecond. So to reach further as a UTP, it will take further 1 microsecond. So that is here total from this respect we can say that whenever this minus 2 volt, it is starting at 0 time. So to reach here as a plus 1 volt, it is taking 3 microsecond of the time. So at this moment at 3 microsecond it is going to show you that this is going to change VO1 from minus Vsat to plus Vsat. So here I can say that this is minus Vsat, this is minus Vsat and this is here plus Vsat. So at this point this is going to change here from minus 10 volt to plus 10 volt as per the specification given. So again it will maintain to this plus 10 volt or plus Vsat till what time? Till the lower trigger point. So up to this point it is maintaining here as a plus 10 volt here. Up to this point it is maintaining here as a plus 10 volt here, and again here at this point whenever this input is going to change or whenever it is going below of this LTP as a minus 1 volt, by that time again the output of the first op amp as a VO1 will change from plus Vsat to minus Vsat. So here it is going to change like this, and again this will be maintaining at low till the further this point wherever it is becoming that 1 volt. So till this much of the point it is going to hold this minus Vsat or minus 10 volt, and again transition will takes place at this point, and by that way it is going to repeat this waveform producing this square wave with the peak of plus 10 volt minus 10 volt. So now if we'll compare this when the output is produced, so here if you'll see that this output, this is what I can say it here. This is VO1 output. First waveform is input waveform and their corresponding output it is giving here VO1. So if we'll compare here with respect to the input when the output is produced. So here if you'll see that this is the time when this input is crossing their zero line, and this is the time at which their VO1 is crossing their zero line. So here this is 0 volt line and this is time axis here. So if you'll see that after how much time it is crossing this. So 0th line for the input it is cross at 2 microsecond with respect to minus 2 volt is reaching to this 0. Here this minus Vsat is going to cross this 0 point at 3rd microsecond. It is transiting from minus Vsat to plus Vsat at 3rd microsecond. So with respect to this input, when the output line is going to cross this 0th line, we can say that after 1 microsecond delayed with respect to the input. So here the time period for this one also we will have same. It will be 8 microsecond only. But with respect to this 0 crossing line, if you'll see that after how much time it is producing the output, it means we can say that it is the delayed version with respect to the input is 1 microsecond. So what I'm going to conclude here for this part, that output of the first op-amp is produced as a square wave with respect to the input of this triangular wave. So triangular waveform is the input for that Schmitt trigger circuit. As per the functionality of the Schmitt trigger circuit, it will produce a square wave but not parallelly at the same moment. It is producing the output after 1 microsecond delayed. That how we can compare that? When this input is crossing 0 line and when it is and when this VO1 is crossing this 0 line. So with respect to this input, like input is crossing 0th line at 2 microsecond, but VO1 is crossing this 0 voltage line or ZCD at 3rd microsecond. It means it is 1 microsecond of the delay. So what we got this from this waveform analysis, that output VO1 is the square wave as a 1 microsecond delayed with respect to the input whatever it has provided as a triangular waveform as input to this Schmitt trigger. So if you see that delayed is compulsory for this circuit, it means option B and C cannot be the right answer here. Now we have to check it with option A and D. So first of all, this option B and D cannot be correct because it is showing here not delayed, but as per the analysis we got that the output of this first op-amp is delayed with respect to the input. By how much time? So that time we got it there as a 1 microsecond. So as per that, this A is also not correct. It means that as per the selection and rejection, we can say that this option D is the right answer without finding the second portion of this question itself, because in the exam we have to save our time. So obviously it is giving that VO1 is delayed by 1 microsecond related to VI and VO2. So this this second op-amp is what? Second op-amp is integrator circuit. So that is going to integrate what? It is going to integrate this square wave, whatever is the output from the first op-amp is given as input to this second op-amp. So that will produce here the waveform as a trapezoidal waveform. So VO2 will be trapezoidal waveform and this VO1 output will be the delayed of 1 microsecond with respect to VI, but the output will be a square wave. And here the input for the first op-amp is triangular wave. So by this way we got the right answer for this question is option D, and by this way this is the end of the explanation for this question. Thank you. So the question here is, in the circuit below the op-amp is ideal and this is the circuit given here, and if the circuit is to show sustained oscillation, the respective values of R1 and the corresponding frequency of oscillations are. And their answer is given in all these four options of A, B, C, D. And here, this is the question it has taken from GATE EC 2024 from the subject of analog circuit. So if you'll observe this circuit here, then this circuit belongs to oscillator circuit. So this question is taken from the oscillation, and here if you'll observe that this first part or left side, it is basic of this circuit. Here it is called amplifier portion of this amplifier of this oscillator circuit, and this second part it is called as a feedback network. So as we know that for the oscillation there is feedback network is also required apart from the basic of the amplifier. So in this question we have to find out, to sustain the oscillation, what should be the values of R1 in terms of R, and what will be the frequency of oscillation. So these two things we have to find out in this question. So as we know that the condition for sustaining the oscillation, that it is given for oscillation, for performing oscillation, or we can say that to sustain oscillation, that condition is A into beta is equal to 1, where A is the gain of the basic of the amplifier of the circuit and beta is called the gain of the feedback network. So if you observe that whatever is the op-amp as a first portion, it is used here in terms of, I can say that it is working in non-inverting amplifier. So for the non-inverting amplifier operation of this circuit, it is giving here their gain as A is equal to 1 plus R1 by R. Let's say this as a equation number 1, and the next part we have to find out that beta. So now we will perform calculation of beta. Calculation of beta. So we can remove, like what I was trying to say, that if you see that left portion of this circuit here, it is the basic of the amplifier which is working in non-inverting mode. So their gain will be, for this portion their gain will be A is equal to 1 plus R1 by R. And now we have to remove this second portion which is called feedback network. So we can consider this output of this op-amp is V0, and this point voltage is called here as a VF. So we know that for the feedback network, their network gain beta, how it is defined here, VF by V0. So now we have to perform the calculation for this beta. So we have to remove this second portion which is called as a feedback network to find out their feedback gain as a beta that we are going to perform in the next. So here, if we are going to remove this portion of the circuit, then the circuit will look like this. This is the capacitor. This is here one resistor, whatever it has taken. This is the another resistor, and the common ground we can separate here. And this is the second capacitor. So this node point we can say it here as a VF. VF is feedback output voltage, and this is V0, which is the input for this feedback network, which is the voltage which is taken from the output of the op-amp. And in the Laplace form, we can write this capacitor in this way: 1 by SC. This is here R, this is here R, and this will also be 1 by SC. So now we can apply Thevenin to the first portion. Our target is to calculate their beta. So beta is given here, as we know that as per the definition of the beta, it will be taken here VF by V0. So from this circuit we have to find out this ratio VF by V0, which will be beta, and A is already known in this equation number 1. So we have to put it this, and then we have to take the product of A into beta, which should be equated to 1 here. So now we need to apply Thevenin at this portion. apply Thevenin. So here it means we need to find out the voltage across this node point, or we can say that the voltage across this R will be Thevenin voltage, and whenever we will make the short of this V0, then by that time we can find out their impedance. So we can calculate here this ZTH, we can calculate this ZTH, which is called Thevenin impedance. So this will be given R into 1 by SC divided by R plus 1 by SC. So this will be giving here as a R divided by 1 plus RCS. Let's say this as a equation number 2. Now we can calculate their VTH also. So VTH will be the voltage across this R here. So VTH is equal to R divided by R plus 1 by SC into V0. So after calculating this, we will get it here as a RCS divided by 1 plus RCS into V0. So let's say this as a equation number 3. And now we can redraw this circuit by taking this ZTH and VTH. Then circuit will be look like this. So here this is ZTH, this is here remaining R, this is here another capacitor, and here we are taking this as a VTH. So this in terms of Laplace it will be 1 by CS, this is here R, this is here ZTH, and this is here VTH, which will be given here as a VTH is equal to RCS divided by 1 plus RCS into V0, what we calculated earlier. So we had calculated ZTH, VTH, we can use it here to find out this this is here VF. So we can get it here, this VF is equal to what? VF is equal to the voltage across this capacitor where it is shown as 1 by CA, so that voltage is called their VF voltage. So VF is equal to 1 by SC divided by R plus 1 by SC plus ZTH into this VTH. So now we can substitute the value of VTH and ZTH in this equation. Then this will be giving here as a 1 by SC divided by R plus 1 by SC plus ZTH value we can substitute from the earlier. So this will be given R by 1 plus RCS into VTH value will be what? RCS divided by 1 plus RCS into V0. So from here we can easily find out the ratio of VF by V0. So that will be giving here so that is giving here as a beta. So that beta will be given, this beta is equal to VF by V0 is equal to SRC divided by SRC whole square plus 3SRC plus 1. Let's say this as a equation number 4. This is our equation number 4. So now, as we had seen, for sustaining the oscillation, what is required for oscillation, as we had seen in the beginning condition itself, for oscillation A into beta, it should be 1. So A is the gain of the amplifier which is working there in the non-inverting mode. So that is given there as a 1 plus R1 divided by R into beta value we can substitute from this equation number 1. So this will be giving here SRC divided by SRC square plus 3SRC plus 1, and this is equal to 1. So now if you do that cross multiplication for this one, then we will get it here. 1 plus R1 by R is equal to SRC square plus 3SRC plus 1 divided by SRC. So if you perform this calculation here, then this will be giving SRC plus 3 plus 1 by SRC. So now we have to substitute S is equal to J omega. Put S is equal to J omega in this above equation. Then we will get it here. We will get it here. 1 plus R1 divided by R is equal to J omega RC plus 3, and here for the third term if you substitute here as a J omega, and if you multiply denominator numerator by J, so as we know that J square is equal to, so here what I am trying to say, here we can multiply by this J, and denominator also we can multiply by this J, so J into J square is equal to minus 1. So this can be written here 3 minus J divided by omega RC. So now we can keep that imaginary part one side and real part one side. So this can be written 1 plus R1 divided by R is equal to 3 plus omega RC. I am keeping this J term together, so omega RC minus 1 by omega RC into J. Now you can compare left side and right side term. So if you see that left side there is no imaginary term, so this is having 1 plus R1 by R, so this is the real term. We can compare to the real term of the right side, so it is 3 here. So now this could be even, or this can be written 1 plus R1 divided by R is equal to 3. So from here you'll get it that R1 is equal to 2R. So this is the condition, we got it here as the first part of the question. R1 is equal to 2R is the condition for sustaining the oscillation for the oscillator circuit. Now by equating their imaginary part to 0, because left side there is no imaginary part, so this right side imaginary part can be equated to 0. From there we will get that frequency of operation. So here we can make it imaginary part 0. Imaginary part is equal to 0 because left side there is no imaginary part. So this was the real part only. So imaginary part 0 means we can write it here as a omega RC minus 1 by omega RC is equal to 0. So this can be written omega RC is equal to 1 by omega RC. So from this one we will get it here that omega square is equal to 1 by R square C square. So from this one we will get it here as omega is equal to 1 by RC, because this frequency cannot be negative, so that we are taking only positive sign. So this omega, like we can write it here as a 2 pi f is equal to 1 by RC. So from here we will get that frequency of oscillation in terms of hertz as a 1 by 2 pi RC. So this is the second part of the question, that frequency of oscillation for the given oscillator circuit is f is equal to 1 by 2 pi RC, and the condition is R1 is equal to 2R. So these things we need to match with the option. then we can find out which one will be the right answer. So here we got that R1 is equal to 2R, R1 is equal to 2R, and we got that frequency of oscillation is equal to 1 by 2 pi RC. So just we can match this with the option. So here R1 is equal to 2R and F is equal to 1 by 2 pi RC is matching this value with the option B. So option B is the right answer for this question, and by this way this is the end of the explanation for this question. Thank you. So the question here is, in the circuit shown below, the transistors M1 and M2 are biased in saturation full stop. Their small signal transconductances are GM1 and GM2 respectively full stop. Neglect body effect, channel length modulation and intrinsic device capacitances full stop. And this is the circuit given for this question. And here the rest part is assuming that capacitor C1 is a short circuit for AC analysis, the exact magnitude of a small signal voltage gain V out by V in, their magnitude is, fill in the blanks. So their answer is given in all these four options A, B, C, D. Out of these we have to find out their correct answer. So this is the question they had asked for GATE EC 2024 from the subject of analog, and this question has taken from the topic of amplifier, in which we have to find out the magnitude of their small signal voltage gain. So now if you observe this circuit here, then this M1 transistor is here. If you see that their drain and this is their drain and this is their gate which is sorted together, this is saying that this M1 transistor is operating in saturation region, which is mentioned in the statement of the question also. Here this M1 and M2 are biased in saturation. So if you see that, like whenever we have to find out their small signal voltage gain, it means we are talking about that their AC signal gain. So it means for the given circuit we have to draw their AC equivalent circuit. So first of all, for this M1 transistor, their small signal equivalent circuit will be given like this. This is showing here the transconductance GM1. So here this can be written 1 by GM1. And now if you see that these transistors, whatever we got their transconductance as GM1 and their equivalent is 1 by GM1 for this transistor, which is connected in series with this RB, and this combination is connected to the gate terminal of this M2 transistor. And as per the statement it has given, under the AC analysis or under the AC equivalent circuit, this C1 is short circuited there. So this we will consider this rest of the part as a RS, then V in, and the AC equivalent of this M2 transistor. So by taking all these into the consideration, now I am going to draw their small signal equivalent circuit first, and after then we derive for this voltage gain as a V out by V in, their magnitude. So here there is small signal equivalent circuit for the given circuit, whatever it has given in the question. So here first of all we will get this. This is RB, which is in series with 1 by GM1, which is equivalent circuit element for that transistor M1. So now here this is the gate terminal for M2 transistor, and here this side we can make it, this is the dependent current source for that M2 transistor and their source. So if you see that source for M1 transistor, M2 transistor, both is at the ground, so we can take it here as a common ground. And this is here drain for this M2 transistor. So here as per the rest part of this element, if you see that output part, so under this AC equivalent, this is here the RD, this is the RD, and as a AC equivalent circuit, all the DC voltage should be taken into the as equivalent of ground. So this will be here ground, and at this terminal we are going to calculate their output voltage. So here this is the dependent current, like which what we can say as a drain current. So for this M2 transistor, their drain current is given here as a ID is equal to GM2 VGS. So what will be the VGS? This is their gate, this is their source. So this is the voltage appeared, which is called gate to source voltage for this M2 transistor. And here rest part is like for the source, whatever it has given as a voltage source. So as a practical voltage source or signal source, we have the rest part as a RS here. So this is RS, and this is here a small signal voltage, what it has mentioned as a V in. So now first of all, by applying that KVL here at this input side, we can easily calculate their VGS voltage, or even we can apply voltage division rule to calculate this VGS here. So VGS will be what? VGS is, this is our gate terminal for the M2 transistor. So we have to calculate that gate voltage with respect to the ground, what we can say it here as a source. So that is called VGS. So whatever due to this V in, whatever is the current flowing through this, like this V in, RS, RB, 1 by GM1, these all are in series. So we can easily calculate this node voltage, gate voltage with respect to ground, which is called here as a VGS. So we can easily apply the voltage division rule here. So we can say that this VGS is equal to RB plus 1 by GM1 divided by RS plus RB plus 1 by GM1 into V in. Let's say this as a equation number 1. Now if you see that this output part, so here at this output side, if you see that the current is passing, this ID is passing through this RD, so you can apply that KCL at this V out node point. So we can easily get that this V output is equal to, this V out is equal to minus GM2 into VGS into RD. So let's say this as a equation number 2. So this GM2 VGS is the current passing through this RD. So as per their voltage polarity, this will be plus, this will be minus here. So this V output voltage, we will have it here as a minus GM2 into VGS, what is the current flowing through this RD, and their resistance is RD. So we got this equation. So now we can substitute the value of VGS from equation 1 into equation 2. Then what we will get it here? So this is giving here V out is equal to, this V out is equal to minus GM2 into RD, and the value of VGS we have to substitute from this equation number 1. So we can put it here. We can put it here RB plus 1 by GM1 divided by RS plus RB plus 1 by GM1 into V in. So here the gain is defined as like V out by V in. So here we will get this V out by V in is equal to minus GM2 into RD into RB plus 1 by GM1 divided by RS plus RB plus 1 by GM1. But as per the question, what it has asked about their magnitude only. So here, whenever we are going to take their magnitude for both the side, then this minus sign will be omitted, and here we will get it. This V magnitude of V out by V in is equal to GM2 into RD into RB plus 1 by GM1 divided by RS plus RB plus 1 by GM1. So this is the expression for the magnitude of this voltage gain, what we got it here. So now we have to compare this expression with the given option. So if we'll compare this, then we can find out here that option B is the right answer for this question. So by this way, this is the end of the explanation for this question. Thank you.